Good afternoon, everyone. This is Tony Okeke. I'm a machine learning engineer here at Moberg Analytics. Welcome to the 13th edition of our case studies in Neurocritical Care AI webinar series. To give you some background as to why we're doing this, treating traumatic brain injury is a big mission, and our goal is to help you get up to speed with the tools that are available to leverage AI and the wealth of publicly available data to continue to advance this field and to help us make progress with our goal of improving care for patients with brain injury. We've been organizing this webinar series to show you a series of tutorials and case studies with examples that include actual code to give you the tools to use these data and tools in your own experiments. And we also have a starter grant program where our goal is to try and help you bring your projects to the cloud so you can leverage the suite of tools that we've been developing to deal with all of this data and deploy these models to kind of get your projects up and running as seamlessly as possible. We really do want your feedback. We want to hear any questions or suggestions for improvements you have. If you have any feedback about this specific talk or about the webinar series in general, please don't hesitate to reach out. You can use the QR code here or reach out to us at this email address. If you're interested in suggesting topics and speakers for future webinars, or if you yourself would like to speak at one of these, please don't hesitate to reach out. We'd love to hear from you, and we'd love to have some of you host and lead these webinars yourself. Here's a list of the 12 previous sessions we've done. The recordings for all of these are up on our YouTube channel, and they're all listed on our website here at moberganalytics.com/webinars videos. Go through these. There's a lot of really cool topics that we've covered. Last month, we did a really interesting series on artifact detection for ABP data, and all of the code and resources for these sessions are also available on our website. If you haven't already, you should have received instructions to download the assets for this tutorial and to gain access to Moberg Connect, where we give you access to data set that you can play around with and run a couple of experiments on that comes from the Boost2 trial. If you haven't received access to this or you would like to request access, please reach out to us at craig@moberganalytics.com. And if you have any questions during the webinar, please feel free to ask them using Zoom's Q&A feature, and we'll get to all of the questions towards the end of the webinar. Today, we have a wonderful speaker lined up for you, Florian van Leeuwen. He's a PhD candidate in statistics at the University of Utrecht, where he's part of the Missing Data and Bayesian Statistics research groups. He previously worked at Leiden University Medical Center, where his projects focused on traumatic brain injury, and his work there led him to working with us as a visiting researcher this past summer. It was a pleasure to have him here, and he really contributed some really meaningful work while he was working with us. His current research focuses on prediction models for tabular and time series data, particularly in cases with sparse information and missing data. Today, he's going to talk about some work he's been doing to explore the use of time series foundation models in forecasting ICP waveforms. And I'll let you take it over from here, Florian.
Well, thank you for the nice introduction. I made an introduction slide myself, but I guess I don't need it anymore. Yeah, so today I will be talking about, I guess I'll start off a little bit general about clinical prediction models. The title of the talk is Transforming Raw Data into Clinical Predictions from Development to Implementation. And I kind of want to go step by step through the process of how we obtain a clinical prediction model. So, well, you already gave the introduction, but like you said, I'm a PhD student at the University of Utrecht, and my research focuses mainly on prediction models when there is sparse information. So this can be highly dimensional data or time series data, and in most cases, we have a very small sample size. And like you said, I focus on missing data and Bayesian statistics. Previously, I worked under Ewout Steyerberg at the LUMC, the Leiden University Medical Center. Ewout actually recently moved to the Utrecht University Medical Center, and we worked together on prediction models, specifically in the context of traumatic brain injury. And over the summer, I had the great opportunity to visit Moberg Analytics. We worked on a project that we'll discuss today. So for my prior education, I have a master in statistics, which means I have no medical background. So I won't really dive into many medical questions in this talk. For example, why we use certain X variables or predictors. I will mainly talk about choices you make from a statistical perspective. So let's begin. Why do we want to have a prediction model? Well, usually when a patient enters a hospital, we kind of try to measure what their state is currently, and we might want to get an idea of what their state will be in the future. Obviously, we don't have any idea how it will be in the future, but we can get an indication. So in example of intracranial pressure, ICP data, here we see a graph where on the x-axis is time and on the y-axis ICP, and we see some values. And now we might wonder, in the next 30 minutes, will the ICP say kind of the same or will it shoot up? So it would obviously be great if we can get an indication of which of these two scenarios it will be, because we might want to allocate a different treatment based on our knowledge. So how do we obtain a good clinical prediction model? Well, there are many different guides. I will use one, which was written by Ewout. It has 7 steps to create a good prediction model, and I condensed it to 5 for this presentation. So the first step is about data. Obviously, we usually only have 1 or maybe 2 data sets, so we really have to think about what is in our data sets, which variables do we have, and what kind of population does it represent. Then there are some modeling approaches. How do we deal with missing data? What kind of prediction model do we want to choose? After we chosen a model, we can look at the internal model performance. So in our setting, how well does this model perform? And then what's also very important is the external model performance. So how well will the model perform in a new setting? Lastly, if we are confident that the model will perform well in a new setting, we can think about deployment. So we'll run through these steps and kind of, I'll give you my ideas about these steps and how to implement them. And lastly, I will kind of end off with this example of predicting intracranial pressure. And I will also run through these steps and see how we have implemented these steps in practice. So to start off with the data. Usually we have a data set with some X variables and some Y variables. I chose some things here, but often we see age and smoking, and maybe we have some ICP data. And then we have a Y value, which might be GOSC at 6 months. So how well is the patient at 6 months? Now, the outcome is often some sort of, maybe it's a binary outcome like alive or dead, or it is an ordinal outcome, which indicates how well a patient is doing. But usually what we're really interested in is his health. So we have this kind of latent variable, which is health, and we kind of try to measure it through a proxy, such as an ordinal scale for GOSE. And then we also have a population. So we have some data which stems from a population. And we really need to think about how our population looks and how this might impact the prediction model. So let's say that we have a population of severe TBI patients, and we actually are interested in a population, or our target population is all mild and severe TBI patients. If we develop a model only on severe TBI patients, can we then use it for also mild TBI patients? So this is something I think is very important to think about when you look at your data, kind of what is my population and does it suit well in a setting where I might want to implement it. Now, these are variables and our populations come together and we pre-process the data. And when we have some clean data, we might continue to the data analysis. And there's a really nice paper, I think, which kind of, it is a bit statistically written, but it kind of looks at where uncertainty comes from in this whole process. So why we might be more unsure than we think when we have a data set and we have a population. So for the modeling approaches, um, I think the most important thing when we think about choosing the right model is how can we answer our research question? So, and the big thing there is predict versus explain. So often when we make a prediction model, there might be some strings attached. For example, the person who might want to deploy the model needs to be certain how the relationship of X is to Y. If this is the case, then we cannot really use a very much black box model because then you cannot see this relationship. But if this relationship is not very important to show, then you might use a very difficult neural network where it's not very clear what it's doing, but your prediction might be a little bit better. So when you think about the modeling approaches, I think it's very important to think about what kind of your objective is and how we might reach that conclusion. So how do we handle missile data is also a very important thing. Obviously, when you work with real data, missing data is almost everywhere. And we really need to think about what kind of missingness is there and how can we solve it. Because it would be a waste in most cases to only use rows which have complete data, because then we obviously don't use a lot of data, but sometimes it's very difficult to use, to impute this data. So we can think about this and how can we do this well. So now to what model do we use? Well, there are obviously many different models. I think in clinical prediction models, the most commonly models is probably logistic regression, but there are also tree-based methods of Bayesian neural networks. And I think you see now that there's a lot of weight given to using very advanced models. Well, sometimes that's really not very beneficial. If the relationships in your data are quite easy to model, then it's probably better to use an easy model. And there's this really nice paper from Ewout, which says machine learning algorithms perform no better than regression models for prognosis in traumatic brain injury. And there it's only one case study, but they do show that if you compare some difficult models with more easy regression models, then the more difficult models do not perform very well. And actually, you see this quite a lot for tabular data, that these very advanced neural networks not always work that much better. There's also this nice paper that shows it compares deep learning methods to tree-based methods and also logistic regression, but they show that XGBoost, which is commonly used, actually performs very well in a lot of tabular settings. But often, sometimes your research question allows us to use very difficult data with difficult relationships, and then it might be useful to use a more extensive network or model. For example, the work from Shubayu shows that if you have many variables and you have time series data and you want to use it all in one model at once, it's probably helpful to use a more complex model to allow for these degrees of freedom in your predictions. All right, so let's say that we've chosen a model, then obviously we need a way to check how well this model is working. So there are many different metrics we can consider depending on if we predict a continuous outcome or a binary outcome. We can look at things like R squared, mean squared error, balance accuracy or AUC, and calibration. So I think calibration is something which might not always be discussed, but it's actually very important. What calibration does is it shows us the ratio of predicted risk versus their observed risks. So if you have a group of similar people who all have a 10% predicted risk, do 10% of them actually get the outcome? And this is very important when the goal of the prediction model is to interpret this risk. If it is to make a classification, then it's not so important. And there's also this nice paper about, or from Ben van Kalster, about the calibration. So if you work with clinical prediction models and you have a binary outcome, then I really would stress that this is a very nice read to do. And what's also great to do internally is to do some uncertainty estimation. If we are in a Bayesian framework, then this is, inherently happens, but quite often we are not. We're more in a frequentist framework, and then we can do things like cross-validation or bootstrap to obtain some uncertainty estimates. So if our population would change a little bit, how much would that change our outcome metrics? Now that we have internally validated our model, we probably want to know, will this model work in another setting? And a big question is always, when do we think the model is good enough to implement? So this is almost an impossible question to answer, but what we usually do is we test it on an external database, we do external validations, and then we just empirically see what the model performance is. So how many validations should we do? Is one external validation enough, for example? Well, I want to show an example here of this is a clinical prediction model, the Crusade model, and it has done one external validation with an AUC of 0.82, which is considered pretty high. And the confidence interval is also quite small. So do we now think that this is enough to say that this model can be used in another setting? Well, if we look at the other external validations of the model, then we see that the AUC actually kind of goes all over the place, depending on which setting we are in. And this is largely due to the heterogeneity between the settings. So is one external validation enough? No, because there's too much heterogeneity. And the heterogeneity here, it is context dependent. So depending on what kind of model you use or what settings you look into, this differs. But the problem of this heterogeneity is that it's very hard to solve. You can think about it that the case mix might be a little different between these settings, or the hospital might be a little bit different. The treatment plans might not be equal, and the way they measure variables might not be equal. So all this kind of variance goes into the external validations, and then it's really hard to see if your model can actually be used in different settings. And this is also why I think a lot more people now do more tailored external validation. So if you want to use a model in your hospital, then you would do an external validation in your hospital after you've developed a model in your hospital. And we have a paper about this phenomenon, what you see here, which is an archive, which kind of shows that even if you have 100 external validations, you still are not very certain about how good a model will work in a new setting. Now on to deployment. So deployment is not something I think about a lot, but luckily over the summer when I was at Moberg Analytics, I could kind of see how that plays. So some things which are important are the time and compute it takes to make a prediction. You can imagine that if you have a very large model, which takes a lot of resources and time to make a prediction, that it might not be great to use this in a bedside situation. Also, it's very important to see how the prediction is displayed. So how do we want to show to a practitioner that what our predicted value is? And more importantly, also, how can we show our uncertainty about this prediction? And lastly, in an ideal situation, it would also be very nice if we could kind of update the model for each patient. So how would that work? Well, let's say that we have a patient's ICP data, and we have an already trained model, a general ICP model, and we make a prediction at time point 0. What we could then do is use this data from this patient and update this model. So we update the general model, and then we have kind of a local model, and we can make a prediction at time point 1 for this patient. So then we have kind of a prediction specifically tailored to this patient. So this would be an ideal case. And now I kind of want to go through the example of what I worked on over the summer and kind of show you the steps that I took. So this is the examples about ICP prediction. More specifically, we had a research question is, can we make a reliable forecast for ICP for the next 30 minutes? We thought this was a good time horizon because that would mean that you still have time for an intervention. And for our model, we only used ICP as the input variable. This might be a little bit of a naive approach, since I think it's been shown that a lot more things are related to ICP. But obviously, it is very nice if you would only need to record ICP to make a good prediction. That means that we are much less relying on other values. And there's already been a lot of work in predicting ICP. There's this great review out there which looks at different models which perform forecasting, but also perform outlier detection. And they have a great overview. So if you are interested in prediction models for ICP, then I would definitely give this a read. So let's look at the data. We used the track TBI data set, where there were a total of 83 monitoring sessions from 32 patients with a little over 5,000 hours of data, and we thus have time series data. So we follow kind of the ICP trend over time for each patient. If you then look at the graph for kind of how long the recordings are, we see that there are a couple of recordings which are really long, like 500 or 600 hours, but most recordings are around 20 to 30 hours. And we see that we don't have that many patients, right? We only have 32 patients. That's good to remember. Now for the modeling approaches, the first step what we need to do is to clean the data. So the ICP data is often very noisy. So what we need to think about is removing outliers. You can think of these outliers maybe if there's problems with the sensor, or if the sensor is not correctly hooked up to the monitoring system, then you might see some weird values. And there might also be some missing values. So what we did is we actually implemented a smoothing algorithm from this paper, which they proposed. I won't dive into it very deeply, but the general idea is that first you take out very extreme values, and afterwards you kind of run through the time series, and then you say, look in the next 15 minutes, are there values which are extremely off from the rest of the values? And then what we also do is we downsample the values a little bit. So we start off with values at, I think, having 200 observations per second, and we downsample it to having 1 observation per minute. And this is done because it's else it would be very computationally expensive to make a prediction with such high dimensional data. So now let's have a look at if it actually works. Well, this is just one example, but this is for one patient where on the top we see the raw signal, at the bottom we see the clean signal. And you can see that at the top, the ICP range is between 0, maybe even minus, and well, maybe 450. And we know that these values are not reasonable. So I think, let's say it again, I don't have a medical background, but I think when I spoke to the people at Moberg, we kind of decided that a good range would be maybe between 0 and 80. So then we remove everything which is above 80. And then if you look at the clean data, we see that when this smoothing algorithm has done its deed, then it's showing kind of a more realistic scenario for ICP data, while still having some very high peaks. So that's really nice because that's what we want to keep in the data. Now the general idea which we had when we started this project is well, how can we get a model that forecasts ICP values well? And this is very difficult because it has been shown that it's very hard to really forecast these ICP values. And we don't have that much data. We only have 32 patients. So then what we came up with is the idea of using foundation models. So these foundation models are pre-trained neural networks which have some prior information. So if you think about it from a Bayesian perspective, the idea would be is that we would use an informative prior based on some other training procedure. And the nice thing about these foundation models is they can help in situations with limited data, which is our case. And actually, there's this really nice review paper in Nature where they talk about the benefits that foundation models can have in medical settings. And it has also been shown that these foundation models actually work. So there's this TAB-PFN model, which is a classifier. It's a transformer model, which does classification tasks with tabular data. And they train this model with only synthetic data, and it shows to perform very well in real life situations. But we did not have tabular data. We had time series data. So the start of this year, a new paper came out which talked about creating a foundation model for time series data. It's called Moment. And the data is quite large. It has 385 million parameters. It's trained on 13 million unique time series from different domains. And it's trained on multiple tasks: forecasting, imputation, and anomaly detection. And for our part, we only focus on forecasting. But how is this model exactly trained? Well, the general idea is that it uses these these time series, and then it masks as part of it. So you end up with some parts where it doesn't know the time series and other parts where it does. Then it encodes this information, and then it tries to reconstruct this with a reconstruction head. And it kind of tries to minimize this process. And this is called self-supervised learning. And when we want to implement this model, so this is how it's being trained. And when it's trained and we want to implement it, we actually only encode our data. So we have this full time series, which we encode, and then we add a prediction head here to make a prediction for the future. And we have to train this prediction head. That's the only part we need to train of the model. The rest of the weights and biases are fixed. Obviously, this was not the only model we used. We also wanted to compare it against some other models for our specific task. So we chose to use one more traditional model from the statistics literature and one more traditional model from the machine learning literature. So we have the exponential smoothing algorithm, which is more statistical, and the LSTM, which is more kind of the machine learning world. And I think it's very important to look at the red things. If we start from the left, we see that only the moment model uses transfer learning. So all the other models have no prior information. For the moment model, the input length is fixed at 1212. So this is actually not great because this means that we cannot use an input which is smaller than 512. So it would like to see the previous 512 observations. But this is not great because maybe we want the model to work quickly. So we don't want to wait, in our case, 512 minutes to make a prediction. So we need to think about a solution for that. And what happens is that we just use 60 values and then we just add zeros for the rest of the 512 things we need to put in. So this is computationally very inefficient, but there's no kind of way around it. And what's also very important to note is that the moment model is univariate. So we only chose to use ICP as input for our models. And then that choice was made based on the notion that we could only use one variable in this moment model, and we want to make a fair comparison. And so the input for each models are the previous ICP values from the last 60 minutes. And we try to forecast the values from the next 30 minutes. So now let's look at the performance of the model, the internal performance. So we have some outcome measures. Like I said before, we're doing forecasting, and the outcome measures kind of weigh the distance between the predictions and the observations. So we have the mean squared error, which is just the squared error, and the mean absolute error. And we use these two terms. We train the model with the mean squared error, but it's kind of hard to interpret. And that's why we use the mean absolute error, because it's a bit nicer to interpret. So for the data split, we split the patients up. So we kind of split by patient to make sure there are no data from one patient in the training and validation set. And then 80% of the patients get put into the training set, 20% in the validation set. And then we do 5-fold cross-validation to make sure that we kind of understand how the model works. So now let's look at some results. This is just the average over the 5 cross-folds. If we look at the top 2 rows, the mean squared error and the mean absolute error, we see that the moment model performs best for both. It has the lowest values, which is what we want to see. But if we then look at the mean absolute error, it is 1.78. And if you think about the range of ICP values, which are usually somewhere between, let's say, 5 and 20, or maybe 5 and 15 even, then this value is actually really high. So that is not great. And what we also can see is then if we look at the 90th, or maybe it's even better to look at the 99% of the mean absolute error. So these are kind of the 1% worst performing sections. Then the mean absolute error is almost 9.5. So it's completely off in these sections. So this is something that we do not want to see. So even though this moment model performs the best, all the models actually don't perform that well. But so we were interested by this result, and we actually wanted to see if we kind of can visualize or dive deeper into where the model makes wrong predictions. So what we did is we looked at all the different segments that the model predicted, and then we kind of want to see what the relationship is between some properties of the segments and the mean absolute error. And in this case, we looked at the variance of the segments, because the variance of a segment indicates how variable it is. So if it goes up, down, it might be very difficult to estimate. While if it's a flat line, it might be a little bit easier to estimate. So in this plot, on the x-axis, we see the variance of the section, and on the y-axis, we see the mean absolute error, and the color just indicates the density of the points. So yellow means here that there are many points there, and dark blue means that there are not so many points there. So what can we see? Well, first of all, we see that most points are in this corner here. And we see the points with the most density. So we see that there are a lot of points with a low variance and a low mean absolute error, meaning that there's a relatively stable section, and in that stable section, the model can predict well. But what we also see is when the variance increases, the mean absolute error also increases. And that's also a reason why at this bottom right corner, there are no kind of dots or almost no dots. Which is very bad because we want for some of these sections which are very variable, we want the model to also make a good prediction. So we kind of see it as the segments become more complicated, the model performs worse and worse. So what we can actually do is we can also look at the predictions for a specific volatile period. And maybe that will give us an idea of how these predictions actually look and why they are not working. So what we did here, we made these 30-minute predictions every 10 minutes for the LSTM and the moment model. Yeah, I mean, if we look at, well, we can start at the LSTM, they kind of look the same, but each color is a new prediction after 10 minutes. And we can kind of see that these predictions just cannot capture everything which is going on in the next 30 minutes. There's kind of a lot going on, and it seems like the model just doesn't really know what to do. So it just kind of predicts a stable line with a little slope. And the same is happening for the moment model. So it does predict some sort of shape, but it just doesn't know exactly how the ICP signal will go. And then what we can also do is we can look at how well the model works for different patients. So as I said before, we had patients, and some of the patients have multiple recordings. So what we can do is we can kind of make a plot of the recordings, and then on the y-axis and the x-axis is the mean absolute error. And then with the color, we can indicate if a recording stems from the same patient. And the size of the recording indicates the variance. So what we can see is, first of all, is that the bigger balls are more on the right side. So again, if you have a high variance in your signal, then the prediction will be worse. And we also see that kind of patients cluster together. So patients with multiple recordings, it seems that their recordings are usually a bit similar, which is also nice to see. So the model works all right for some people, like the person which is down here. And this is also quite okay. But for some people, the model really doesn't work very well. So external model performance and deployment. Well, for external validation, in the project, we actually looked at how well the model works on a different data set, which was used before. But this data set only had, if I remember correctly, 12 patients. So there wasn't that much data. But the results seemed similar. But if you would really want to get an idea of how well it would work externally, you obviously need a little bit more data. And for deployment, obviously you would want to implement the best performing model, but like we have seen here, these models just don't perform very well. So it would not make a lot of sense to really want to implement them. So I would like to show now a little bit of the code to see how we actually work with a foundation model, and also showing you how it works to work with this time series data. I just want to check over my. Can you still see my screen, Tony?
Yep, it's still sharing.
Okay, perfect. All right, so you see the cola?
Mm-hmm.
Yeah. All right. So I just want to show quickly an example. So when you want to use this model, usually you have to install something from GitHub or maybe from Hugging Face. But in this case, the moment model had a really nice, it had a really nice example case of how to use the model. You do need to tweak a little bit and see what exactly goes into the model. So in this example, I loaded the ICP data from one patient. And here's the plot of the ICP values. These are actually the cleaned values because I don't want to go into the cleaning procedure here. I just want to show it kind of in general. And then I can kind of show how do we derive our X and our Y values here. So like I said, we use kind of the previous. So let's say that the ICP signal started here at 0. Then we use the first 60 minutes until 0 as our X variables. And then we use the next 30 minutes as our Y variables. So we use these to predict this section. And what we do then is we just move a couple minutes forward, and then we take a new section for X and a new section for Y. So depending on, this is called a stride length, but depending on the difference between these sections, we can actually get many different X and Y pairs from our time series, which is really nice. But also we need to watch out a little bit that we don't get too many training examples. Because if we take a stride length of 1 minute, then we would get many, many training examples, and it might be computationally very hard to do that. So in our example, once we've transformed this entire time series into pieces of X and Y, we end up with 618 pairs of X's and Y. And for the Y, we see that it has a nice shape of 30, just 30 minutes, so 30 values. And for the X, we see that it has this weird shape of 512. And that's just because the moment model only allows input with a size of 512. If we then look at the one X value, we see that only the first 60 values are real values, are filled in, and the rest of the values are zeros. Also, these values might seem a little small, and that's just because they're scaled. So to actually use the moment model, well, in this case, they build a nice pipeline. And using their pipeline, you can import the model. We can name a task. In this case, it was forecasting, but like I said, they also do other things like anomaly detection. Then we can specify our forecasting horizon. This is something we need to do to make sure that the forecasting head has the right output dimension. We can specify some dropout, which you want in the head, and weight decay. And then these parameters are very important. So like I said, I think what you usually want to do is you want to freeze the encoder. So this is the largest part of the network. Sorry, these two together. These are the largest part of the network, and we really don't want to touch them. I actually played around a little bit with also training these, so retraining the entire network, but that just takes a lot of time and a lot of computational effort. And it kind of, I think, defies the purpose of using this foundation model. But what we do want to do is we want to put this argument to false because we want to train the last couple layers of the network. So we can make a right forecast for our specific head. But you can inspect the model if that's something you're interested in. And just to make sure that we have the right parameters, which are unfrozen, so which we're going to train, we can run this code, and then we see that the unfrozen parameters are the linear weights and the linear biases in our head. So that is all great. Now, training the model, or actually I should say fine-tuning the model, is similar to training any other model. We have some loss function, and we have an optimizer, and we have a learning rate. We specify it for some epochs. And then the only thing that we do is for our epochs, we load our data and we make a forecast, calculate the loss, and then calculate the gradient. And then we just update our model here, and then it loops over it again. So here I just trained the model for 15 epochs. And if we then plot the loss, we can see that the model learns very quickly. So in 2 epochs, it's kind of already stabilizing, and then it just stays stable for the rest of the 13 epochs. And I think this is something which can be expected. It's because we initialize the model with weights which are already pretty good because they are pre-trained. We might think that it just needs a little bit of training to find kind of the right direction. But after it's found that, then it understands the connections well. So what we can do now is we can look at the predictions for each specific segment, which I think is pretty nice. So here I just loop over the segments. Like I said, they were scaled, so I kind of scale the values back and I add all those predictions together. And then what I do is for each segment, we calculate some characteristics. In this case, it's mean squared error, mean absolute error, and the variance. So if you then look at the results, then we can see for each section, we have a mean squared error, a mean absolute error, and a variance. And the nice thing about this is what we can do is, well, first of all, we can obviously look at the general performance of this patient. So here, the mean squared error is 21 and the mean absolute error is almost 3. So this is quite high. But I think the nice thing about keeping these segments separate is that we can then look at a good segment and a bad segment. So here I took the segment with the highest MSE, and here I took the segment with the lowest MSE. If we then plot these segments, then here in the dark blue, we kind of see the history, so the past 60 minutes. And in the light blue, we see the real values for the real next 30 minutes. And then in the orange, we see the prediction. So in the worst segment, you see that the moment model really is all over the place. So it finds it very hard to understand if it's where we are, if it's up or down. And then we see for a good prediction, it just is a place where the signal is a lot more stable. And then lastly, I want to show kind of the plot I made before. So what we can do is we can also look at the variance in these segments. So I'm talking about the variance in this little blue line, and then compare that to the mean absolute error. So these are just it is just some code to make the plot nice, but it's just showing these two things. And then if we plot that, we can clearly see that, again, this relationship holds. There are a lot of segments with low variance, and we see that if the variance increases, then the mean absolute error also increases. And the model just finds it very hard to predict these high volatile sessions. All right, I think that's about it. We wrote a small paper about it. It's on archives, so you can scan the QR code if you want, and you can have a look. If you have any questions about my presentation or the paper or using the foundation model, you can always send me an email. My email is on the left side. And I think that's about it. So thanks everyone for listening. Are there any questions or?
Thank you, Florian. That was a very interesting talk. To get started on questions, I have one. Are there other foundation models for time series that you looked at that maybe could perform better than the moment model?
Yes, I think actually recently there have been a couple of foundation models being proposed. But when I was working on this project, I only knew about one.
Mhm.
But it would actually be really interesting to kind of compare multiple foundation models. Although I think for this task, it might be the case that it's just very difficult to forecast ICP with only ICP. So
Mhm.
there's probably some kind of, well, there's a lot of unexplained variance. And even if you use kind of the most advanced network that there is, a pre-trained network, then you might not be able to explain this unexplained variance.
Mhm. So do you think looking at approaches where you give multiple time series and try to use information across different modalities to try to predict ICP would be promising?
Yes, I think that will be a much better choice. So even using a non-pre-trained LSTM network
Mhm.
with many input variables, which are time series, I think that would be a really good choice. Although if your sample size is small, it might just be difficult to make a prediction model which can be generalized. But
Yeah.
I think that would be very promising, even if you could use a foundation model which allows you to do this.
Mhm. I mean, from the results you showed, you don't necessarily need a foundation model to have good results. A regular LSTM can still do pretty well on this task. So maybe
Yes,
that
I,
would be a good place to start with developing something like this.
I definitely think that you should start with just something kind of more basic.
Mhm.
Especially we do still have some data here. It's just that I think what it's very hard to model is that there's a lot of heterogeneity between patients.
Mhm.
So like you remember the one figure where I showed kind of the recordings of the patients and the mean absolute error, you see that the model performs very differently for different patients. And I think this is just because the patients are very different.
Yes.
So if your data set is not a full representation of your target population, then even if you use a very nice LSTM model, you will still not be able to kind of fully be able to predict all the predictions you want to make. So then maybe
Mhm.
it does make sense to use something like a pre-trained model because that has already some of this information embedded.
That's a good point too. When we were developing the models for artifact detection, we noticed the same thing with the variability between patients.
Yeah.
One thing we did was we took, um, I think, 30 pulses from a patient that we wanted to run testing on and use those to fine tune the model first before doing the rest of the test evaluation. And that did improve its performance. So maybe if you want to forecast ICP for a particular patient and you have clean data for that patient, you can kind of prime the model on that patient's ICP waveform, and that might improve the forecasting performance.
Yes, I completely agree. I think this is a very kind of smart idea to move away from this kind of general model to more tailored towards, well, first of all, towards a specific setting, and then
Mhm,
secondly, towards a specific patient. Because I
mhm.
think that's in the end the goal that we're aiming for with these very flexible models.
Yes. Does anyone else have any questions? Feel free to type them out in the chat.
I see one question in the Q&A. Um, I said it said you showed a few patients where the model was not performing well. Do you think it is a problem of the model or the data? So that's a very, very good question. Um, Actually, in our cleaning process of the data, um, we left the data a little bit noisy. So we could have cleaned it even further, but we decided on that it would be a better representation for kind of for real life scenarios to keep some of the outliers in and do not kind of tamper too much with the data. So what can definitely happen is that some of these outliers were probably in specific segments of specific patients, and maybe these were just kept in. So that would make the prediction test for different people more difficult than for other people. So the data was still very noisy when we put it in. Well, less noisy than before the cleaning, but still noisy. Um, but I also think it's part of it is due to the model, unfortunately, that it just there might not be enough information in ICP alone to make a good prediction.
Any other questions? Well, Florian, thank you again. This was a very interesting talk. Um, are you going to be doing any more work to develop these models or in a similar vein for ICP prediction?
So my main focus right now is working on prediction models in a more general sense. So work more about well, for example, if you have many predictors, how can you select the right predictors? So not
Mhm,
necessarily on one specific field, uh,
mhm,
but I do aim to kind of apply my models in settings like this, where we can clearly see that the prediction probably is very difficult,
mhm.
and there's a lot of benefit of using, I think, some nice models here.
Whenever you have results, feel free to come give another talk. I'm sure we'd all love to hear to see more of your results.
I still see one question. Uh,
I,
It's how long did the model uh, take to train? That's actually a really good point. So when I ran the model on our full data set, so we had what I say I think 30 patients, then to run it for 10 epochs, it took about an hour or an hour and 20 minutes. So it's not very quick. But I think that it's, yeah, so even though we fine tune it, it's still kind of a slow process. And that's also because it's embedded in this kind of pipeline. So it's not really optimized, I think, for being quick. So you do need some time to even fine tune the model. I think there's one more question. What was the most enjoyable part of creating the models, writing the paper? What do you like most forward to with this model or creating new models? Um, yeah, I think it was really nice. I think it's great to play around with these models because, like you see kind of the boundaries which they have. So clearly, it's a very bad limitation that you can only use an input of 512. Something like this is just very annoying. Also, it's really nice to see that each model, or maybe not nice to see, but each model has like a different input shape that they want. So when you compare these models, you really have to think about the shapes of what your data is in and how you kind of can correctly use them for all of them. Um, and of course, unfortunately, we saw that the models did not work very well. But I think that it's actually not a kind of a big problem because, um, well, we cannot decide if a model will work or not. And it's also sometimes really good to see that models do not perform very well or better than more basic models in certain settings. So that's why I think it's actually quite a nice conclusion of this paper. So we say is that in our case, it just did not seem to work very well. And that's also completely fine. I think that was it for questions.
Okay. Thanks again, Florian. I'm sure we'll do this again. If anyone has any questions after this, feel free to reach out to us at Craig at moberganalytics.com. You'll be able to find a recording of this webinar on our YouTube channel and on our website. And please subscribe to the Neuroscience Monitor. It's our monthly newsletter. You'll also be able to see you'll also get the links to the recordings in the newsletter when that gets sent out. Thank you all so much for attending. Have a good weekend and a good rest of your day.